let us start with the second part of today's lecture, which will be about more general class of optimization problems. Specifically now we will also, besides equality constraints, we will also consider inequality constraints. So in mathematical terms, what we have is, we have a cost function that we would like to minimize, and besides equality constraints, we also have some inequalities. And while the equalities, I mean, they are very good at describing real-world phenomena like mass or energy conservation rules, where the sum of input flows must be equal to the sum of the output flows with no accumulation. The inequalities, I mean, they bring new properties of the optimization problem. We might want to find the optimal quantities if we know the lower and upper bounds. And examples of these problems, I mean, you find them everywhere. Really, this is where serious optimization starts. Because we can solve a very general type of problems, and one of them is the so-called allocation problem. Now, don't look now at the specific instance. This is a class of allocation problems where we have some sources, in our case it's the money, that we need to allocate to particular places or people or type of tasks that we are performing. In our case, we have one asset, which is money. We have exactly this amount of that. We have to split it between work and material. If we know that if we allocate X to the work and Y to the material, this is the amount of products that we will sell. And of course, we would like to maximize the number of products that we sell because that brings the maximum profit. If we know that we can, of course, only allocate non-negative amount of money, okay, and we are not allowed to allocate more than 20,000 for the material. Okay, so this is inequality constraint. This is the equality constraint, which says X plus Y must be equal to 60,000. So that's this one. And we have the cost that we would like to optimize. So here we see where inequalities enter. Okay. Another very general type of problems is called the diet problem. Essentially, you would like to cook a very good dinner, and you are required to cook the dinner from some predefined food. Each food has its price and some caloric value. You would like to save as much money as possible. However, you must prepare a food which has exactly 8 calories. Okay? And you don't want to spend more than 10 euro for that. And now you have different food, and you would like to find out the optimal composition of your final dish. Okay? So this is the function that we would like to minimize. That's the total purchase price. It's the individual price times the amount of food that we are buying, such that the total calorie value as an equality constraint is satisfied, and the inequality constraint here says don't spend more than 10 euro for that. Okay? And don't think about maybe food here, but you can, like in a refinery, you can get oil from multiple deliveries. Okay? Each delivery has some purity and some price, and it's up to you to find the optimal composition of the oil that you are buying from different providers. Okay, so that's what the diet problem is about in general. Another type of problems which includes inequalities, and we will have a whole lecture devoted to these kind of problems, is the so-called separation problem. Now, separation can be used for many things, like for instance, face recognition problems. But here is kind of the practical example. Imagine that your company, like the refinery, operates 2 types of units. One is the high pressure units, and the other ones are low pressure units. And you need to find out like a safety wall which splits these 2 types of units from each other, such that if there is an emergency, it doesn't hit the low pressurized units. And we need to answer the problem whether they can be separated or not. Well, if the wall is supposed to be just straight, imagine that also one of these black lines would be here. there is no straight wall which would cleanly separate those two types of units. So the first question is, can they be separated? And if they can be separated, how should this wall look like such that the separation is achieved? And this procedure of separation, which includes inequalities, they can be extended to, say, some kind of circular or ellipsoidal walls. And as I said, we will have a whole lecture on these separation problems. Classification problem is a slight modification of the separation problem, so I will leave it for the separate lecture then. Another type of problems which include optimization with inequalities are so-called logistic problems. So the empty squares here are the customers that your company has to serve, and you are thinking where to put these warehouses such that you minimize the transportation cost and you make sure that each customer is served with the food or materials that he has ordered from the warehouses. So the optimization here decides where should be those warehouses situated such that some equality and inequality constraints are satisfied. Another type of problems which includes inequalities is the transportation problem, as we had it previously. It's just that this time we are also assuming that we also have lower and upper bounds on the limits of how much we are allowed to ship through individual channels. Okay? So we have, of course, the upper capacity, but we might also want to have the lower capacity. Like, we must ship at least 10 tons of oil through this pipe because otherwise the system would not have enough pressure to ship the commodities through the network. Another example of using optimization with inequality constraints is optimal control. Basically, we are using the model of the plant to optimize its behavior. We would like, of course, to minimize the regulation error, which is the difference between the set point in the dash and the actual output of the plant. And we have the current measurements available. We know how the system will evolve. That's the model of the system. And we have constraints on inputs and outputs. So this is kind of a very advanced version of a PID, because we know that a PID controller does not provide guarantee that constraints will be satisfied. Optimal control does provide these kind of guarantees. Okay. So how do we solve these problems? That's where it starts to be interesting. So these problems are very useful, actually. If there would be no methods to solve inequality constraint optimization, optimization itself would not be as successful in practice as it is. So there is a way how to solve these problems, and there is one general way that we will cover now, and then there are particular algorithms that we will cover on subsequent lectures. So the very general way of solving these kind of problems is based on investigating the individual constraints from the point of view whether they are active or not active at the optimum. Now, what does this mean? Let me show you graphically. Okay? So first of all, we are considering this kind of problem. So thing number one that we do always when we want to solve the problem is to convert it into standard form. So first, minimization, which was already done, and then all constraints converted to less than or equal to, and here we have the right-hand side. We could also put the right-hand side to the left, but it's important to have it at least as less than or equal to. Okay? Now imagine that this is now the cost function. These are the level sets of the cost function. It's just a linear function, right? And these are the constraints. Where is the optimum? We minimize the function, so these arrows essentially says which direction do we go. Okay? If there would be no constraints, the optimum clearly is at minus infinity, right? Because we are minimizing x1 plus x2, we could go as far to the left and down as possible to find the minimum. Now the constraints, they stop us for going further. Therefore, the optimum is right there at the corner. And here is now where we can start distinguishing the constraints. Clearly, the optimum here I mean, these are the 4 constraints. So x1 smaller than 1 is this constraint, right? This one is which one? It's this constraint here. It says x is larger than minus 1. This one is this constraint. It says x2 must be smaller than 2. And this one is this constraint. It says x2 must be larger than 0. So what can we say about this constraint? Does the point lie, the optimal point, does it lie on the constraint or not?
Equal to.
So in other words, the optimum is 0 and minus 1. 0 is the x1 optimal. Minus 1 is x1 optimal because this is the x1 axis, and x2 is 0. That's the optimal point. So x1 is minus 1. What is the relation of the optimum with respect to the right-hand side? Is there a strict inequality or is there equality?
Equal.
So we have minus 1 here. So we have inequality here, strict inequality. Here we are considering that x1 optimum is minus 1. Minus times minus is just 1. So this constraint at the optimum says 1 is less than or equal to 1. In other words, at the optimum, we say that this constraint is active because it is satisfied with equality. Okay? This constraint at the optimum is also active because the optimal point lies on the corresponding constraint. However, these 2 constraints are not active because the point does not lie on the constraints themselves. Okay? So we have a situation like this. And this is what we call this constraint classification. We split the constraints into 2 parts. Into constraints which are active at the optimum and constraints which are not active at the optimum. Okay? The problem is we can only do this classification once we have solved the problem. Because if I don't know where the optimal point is, I don't know which constraints are active. Right? What if I hide this star? Can you tell me which constraints are active at the optimum? Well, okay, also imagine that the level sets are not here. Okay? How do we know where the optimum is? We can only analyze constraint activity once we know the optimal point. But now imagine this. I tell you that at optimum, this and these constraints are active. Can you tell me the position of the optimal solution? Well, we have 2 optimization variables. I just told you that 2 equalities must be satisfied. 2 equalities in 2 unknowns is a unique solution. In other words, if somebody would be so kind to tell us these are the constraints which are active at the optimum, you can compute the position of the optimum just by solving a system of linear equalities. The problem is nobody would tell you which constraints are active because nobody knows that until we solve the problem. So it's kind of this chicken and egg problem. Who was first? But we will see that, okay, I don't know which constraints are active, but I can at least analyze all possible combinations. If I do analyze all possible combinations, then I can check which point is optimal and which is not. That's exactly what we will do in a second. Okay? So this is a good case because we have 2 optimization variables and we see that we have 2 constraints which are active at the optimum because we need 2 equalities to get a unique point in 2-dimensional space. Okay? However, this is again a good case. So can you tell me which of these constraints are active and which are not for the optimal point? So that's really the same thing. Okay, so these 2 constraints are active at the optimum and these are not. Okay, so it's the same situation as before. What if I change the objective function such that the optimum is here? Which constraints are active at optimum here? Huh? None of them. Exactly. Yeah. All are inactive. Okay. We can have a situation like this. How many active constraints are there at the optimum? Exactly 1. Okay, and it's the first one. Okay. So now think. What if I would tell you? You don't see the figure, I only tell you constraint number 1 is active at the optimum. Can you tell me exactly the coordinates of this point? No, because we have 2 unknowns and we only have 1 equality. Okay? So there must be some other equations which will tell us exactly where the optimum is situated. And these conditions, so this is just a short summary. So we call a constraint active if at the optimum the corresponding constraint is satisfied with equality. If at optimum the constraint is satisfied with inequality, strict inequality, we call the constraint not active. Okay? And now back to that original question. So what if we have fewer active constraints as there are optimization variables? And these cases can happen. So we need additional conditions. And these additional conditions are called the Karush-Kuhn-Tucker conditions. We have already heard that name when we consider the quality constraint optimization and meet those gentlemen. So actually this whole theory, this was a breakthrough. This was a breakthrough that was made in late 50s of the previous century, so 1950s or something like that, or maybe even 60s, I don't remember exactly. These 2 gentlemen have published a breakthrough paper which has shown how to solve optimization problems with inequality constraints. And everybody started to call this procedure as the Kuhn-Tucker conditions which allow to solve the optimization problem. So that was in the 50s or 60s. Only then somebody discovered that a gentleman called William Karush has published the same result like 20 years before them as part of his diploma thesis. So as part of a diploma thesis which nobody knew about, or very few people were familiar with the result, Karush has discovered a breakthrough in his diploma thesis. And once it was found that it was actually him who has done it first, and these gentlemen kind of separately reinvented. They were not familiar with his results. It was not any plagiarism or anything like that. Okay? Independently, they figured out the same conditions, but just 20 years later. That's why his name was included as the first one in this Karush-Kuhn-Tucker system of conditions. Okay? Unfortunately, I couldn't find a picture of this guy. One of these is American, one of them is Canadian, the other one is for sure American. Okay? So, and what these gentlemen did was they have shown that we can solve constraint optimization problems with inequalities using an extension of the Lagrange theory. Because we have seen that if we have only equalities, what we do is that we form the Lagrangian and we just take the gradient equal to 0. If we have inequalities, this is not the only condition that has to be satisfied. There are more conditions than the derivative being equal to 0. So from the beginning, the Karush-Kuhn-Tucker optimality conditions for a problem with inequalities, they start very similarly as before, meaning we also take the Lagrangian by taking the original cost function plus the Lagrange multipliers multiplying the left-hand side of the normalized constraint. Okay? And then that's the standard condition that we had before. The gradient of the Lagrangian must be equal to 0. But if we have inequalities, there are 3 more conditions that need to be satisfied for a point to be optimal. So the first one is the gradient of the Lagrangian being equal to 0. This condition is technically called the stationarity condition. The second condition means that for a point to be optimal, it has to satisfy the original nonlinear constraints. So this is just the repetition of the same that we had here, it's just that they have to hold also for the optimal point. And this is called the primal feasibility. Then we have the third condition, and here you really have to remember this. When we had a Lagrangian for equality constraints, the corresponding Lagrangian multiplier could be anything. It could be positive, it could be 0, it could be negative. When we have inequalities, the Lagrange multiplier can only be non-negative. Okay? So negative values of the Lagrange multipliers for inequalities are not allowed. And this condition is called the dual feasibility. We will talk about duality later in the course, but that's what is called dual feasibility. And this last one is quite tricky. It says that the product of lambda times the constraint for each constraint must be equal to 0. And this condition has a very strange name. It's called the complementarity slackness. Essentially, you can probably see what happens here. Since this condition here holds, essentially the Lagrangian, this term here is also 0. Right? So by solving the Lagrangian, we solve the original problem. It's just that what happens, in fact, here is that we are introducing additional degrees of freedom, these lambdas, which will exactly help us in situations where we have fewer active constraints than there are optimization variables. Okay? So that's the whole reason why we make this business with the Lagrangian and with these additional conditions. Because often we have fewer degrees of freedoms as there are optimization variables. So these Karushkin-Tucker conditions, they introduce additional degrees of freedom. These are these lambdas, which supplement the missing active constraints and allow us to find the solution. Now, there is a catch here. There is a problem. These conditions, in general, are only necessary, meaning any optimal solution must, of course, satisfy them. But if I just find the optimal solution which satisfies these conditions, I cannot say that this point is the minimum. Because it can still be a maximum, it can be a stationary point, like a saddle point. So these conditions are only necessary. However, if the problem is convex, meaning the objective function is convex, and these constraint functions are also convex functions, then these conditions are also sufficient, meaning if there is a point which satisfies these 4 conditions, it is safe to proclaim the point as the global optimum of the problem. Because the conditions for a convex problem are both sufficient and necessary. So let me illustrate how can we make use of these conditions to actually solve an optimization problem. Let us assume a very simple problem. We have just one optimization variable. And we have these kind of constraints. So x really has to be between -1 and +1, right? We know where the optimum is, right? The optimum is at +1. Okay? But we would like to find the optimum in some kind of general procedure. So what do is first we convert it to this standard form, because we will form the Lagrangian and so on. And that's the Lagrangian that we had, so that's the original cost function, plus lambda1 times the first constraint, plus lambda2 times the second constraint. Now we form the Karushkin-Tucker optimality conditions. The first one is stationarity. Stationarity means the derivative or the gradient of the Lagrangian with respect to individual x's here is equal to 0. Okay? So when we make the derivative here, there's just 2 times x. The derivative of this term here, sorry, where does this 2 come from? Okay, so this is x squared minus 2x plus 1. Okay? So that's the derivative of x squared. This is the derivative of minus 2x. This is the derivative of lambda1 times x1 with respect to x. And this is the derivative of lambda2 times minus x1 with respect to x1. Okay? So here we are only taking the derivative with respect to x, not with respect to lambdas. That must be equal to 0. By the way, our problem, notice, is convex. Because the cost function is minimization of a quadratic function. That's convex, and all constraints are convex as well, because they are linear functions, and we know linear functions are both convex as well as concave. Okay? So the problem is convex, and therefore the Karush-Tucker conditions are sufficient and necessary. Okay? So then we have primal feasibility, which are just the original constraints, repeated. Then we have dual feasibility, which says Lagrange multipliers must be non-negative. And then we have this complementary slackness, which means essentially this term has to be equal to 0, this term has to be equal to 0. Now the problem with solving for x, lambda 1 and lambda 2 is that notice that here we have lambda 1 times x. Both lambdas, so lambda and x, are optimization variables. Therefore, here we essentially have lambda times x minus lambda is equal to 0. That's a nonlinear equation. So that's not easy to solve. Okay? However, there is a way around avoiding these nonlinearities here. Essentially, the way is that we explore all possible combinations of active constraints. Okay? Here, we have two optimization, well, in fact, just one optimization variable. Okay? So what could be the possible active constraint? Well, first of all, no constraints have to be active, right? So essentially, if we are minimizing a function like this, and we say that this is the allowed interval of x, then no constraints would be active at this point, right? Okay? It's just that our problem is like this, where the optimum lies exactly here. Okay? And since we don't know where the optimum is, we have to consider the case where no constraints are active. Right? By the way, why did I put that no constraints implies that deltas are 0? Oh, sorry, the lambdas are 0. What do we say? We say that the constraint is not active. So the complementary slackness condition is like this. Now we are assuming that the i's constraint is not active. If it is not active, that means that it is strictly negative, because that's what a not active constraint is. Okay? In other words, this is a negative number. How can we, by which quantity must we multiply a negative number such that the product is equal to 0? This one must be 0. Okay? No other value will make the product equal to 0. Okay? So that's why if we have a non-active constraint, it means that the corresponding lambdas are definitely 0. The other way does not hold. A constraint can be active, meaning a constraint is active when this is exactly equal to 0. Now, if I multiply it, since this is already 0, I can multiply it by whatever number and still have the product equal to 0. That means if the constraint is active, all we know is that this must be larger than 0. Well, larger than or equal to 0. And that allows both the 0 value as well as a positive value. Okay? So we have this, this first possible combination of active constraints. Which other possible combination we have? Well, we can assume that this constraint is active. Since the constraint is assumed to be active, that means one possible candidate for the optimal solution is this one. We can also assume that this constraint is active, which would imply that this is the optimal point. And do we have anything else? Well, not really. We cannot definitely have both constraints active at the same time, right? Because x cannot be simultaneously 1 and minus 1. Okay? So now we have three possible situations. And we just need to find out for which of these situations these conditions are satisfied. So we have to solve or verify these Karush-Tucker conditions for each of these three scenarios. So let us do that. Okay? So let us first consider the scenario number 1. Okay? So what can we deduce here? So first we are assuming that lambdas are 0, right? So all the lambdas would be 0. If they are 0, then the optimum x from stationarity condition is trivially equal to +1. right? Because this goes away, minus 2 goes there, 2x is equal to 2, x is equal to 1. That's the first candidate for the optimal solution. However, for that to be an optimal point, also all the other conditions have to be satisfied. Just the stationarity being satisfied means nothing if we have inequality constraints. So let us check. Does that candidate satisfy primal feasibility? Yes or no? The first condition, is it satisfied at the optimum? It is. This one is also satisfied at the optimum. Let's check dual feasibility. Do the lambdas satisfy these conditions? They do, right? Because lambdas are 0. So lambdas are dual feasible in this scenario. But we also need to check complementary slackness. Does it hold? Well, as soon as lambdas are 0, trivially, these conditions hold. Okay? In other words, we have assumed this scenario and we have found this candidate. And what now? Well, in general, if the problem is non-convex, we cannot say anything, because the conditions are only necessary. We would need to explore all of them and then find out which of the candidates is really the best solution. However, since the problem was convex, we know that the conditions are sufficient and necessary. Therefore, we can stop here, right? But we will not do that. Let's explore the other options. So let's assume this is now the scenario. So here we have the candidate directly from the assumed activity of the constraint. Right? And again, we have to check that all inequalities and equalities hold. The problem now is we don't know what the lambdas are. They are no longer given. Right? We have to compute the lambdas. How can we compute them? How many lambdas do we need to compute? 2. To compute 2 variables, we need 2 equalities. So we are looking for 2 equalities which involve lambda 1 and lambda 2, which will allow us to compute the values. So what we can do is, well, of course, this candidate is also primal feasible. That's clear. One of those lambdas, we know its value. Lambda 2 definitely is 0 because in this scenario, we are assuming that only this constraint is active, which immediately means the other one is not active. So if the other one is not active, that means the corresponding lambda for sure is 0. Okay? So now we are only looking for the value of lambda 1. We need one condition. So we can use stationarity. We know x, we know lambda 2, we can compute what lambda 1 is. Right? So from stationarity, we will find out that lambda 1 is equal to 0. And here you can see that really we are assuming this constraint is active, but the corresponding lambda is 0. Right? And we are still not done. We still have to check all the remaining conditions. So we have to make sure whether lambda is feasible, dual feasible, and whether the complementary slackness holds. And it does, because lambdas are 0. So this is another candidate, which is the same as in the previous scenario, and since the problem is convex, we can stop here. But we will not do that. Let's explore the third scenario. Okay? So we are assuming that this constraint is active at the optimum, which clearly is the wrong result. But here we will see that the conditions will tell us that, hey, this cannot be the optimal point, because the conditions will be violated, at least one of them. So let's take a look. So the candidate clearly is -1 directly from the assumed activity of the constraint. Right? Then we check whether it's primal feasible. It is. It is in the interval from -1 to 1. Now we need to check dual feasibility, and for that we need the values of lambdas. How do we compute the values of lambdas? Tell me one lambda, which is for sure the correct value for this scenario. Always look for those constraints which are assumed to be not active. So lambda 1 is 0 because this constraint is not active. Therefore, we can again look here and compute the value of lambda 2, because this is 0 and x is -1. So when we do that, we find that lambda 2 is -4, actually. Okay, so this is -2, -2 is -4. This goes away, and the 4 goes. No. It's lambda 2. It's -4 here, and here this goes to the other side. So lambda 2 is -4. Okay. Now we check dual feasibility, and we find out that lambda 2 is not dual feasible because it has a negative value. Therefore, the results of gentlemen Karush-Kuhn and Tucker says us that this cannot be a candidate for an optimal solution, right? So this is how these kind of optimization problems are solved in practice. We basically have to try out all possible combinations of active constraints. The problem with this approach is there can be many combinations. Essentially, how many combinations can there be? Okay, let's leave it for the next lecture. Many. Okay, and let us just test the procedure on one more example. Okay, something more complex. So can somebody tell me, just by looking at it, what would be the optimum here? Well, if we would neglect the constraints, then the optimum is when x is equal to 2 and y is equal to 1, right? The question is, does this solution satisfy constraints or not? So we are saying x is 2, y is 1. This constraint is satisfied, right? But here we have 2 plus 4, that's 6, and we are saying that must be less than 3, and it is not. Therefore, the solution is not so obvious where it is. Okay? So we have to use the Karush-Kuhn-Tucker conditions to actually check all possible candidates. And for that, step number 1, form the 4 KKT conditions. The first one is that the derivative of the Lagrangian with respect to the optimization variables is equal to 0, that's stationarity. For that, we first need the Lagrangian. We know how it looks like. So note that we had to convert the constraints into the standard form, and each constraint is multiplied by the corresponding lambda. Then we take the gradient with respect to x and y, so these are those two stationarity conditions. Then comes primal feasibility, meaning the original constraints. Then we have dual feasibility, meaning all lambdas must be non-negative. And then there is complementary slackness, which means these added terms here, they must disappear at the optimum. So these are now the Karush-Kuhn-Tucker optimality conditions, and let's explore all possible combinations of active constraints. We have two optimization variables, meaning we can have either no constraint active, exactly one constraint active, or exactly two constraints active, right? Because we have two optimization variables, so having exactly 3 constraints active cannot happen because, well, it could if the constraints are linearly dependent. But if they would be linearly independent, it would mean we have an overdetermined system for which there is no solution. Okay? So that's why the candidates are as follows. The first one is no constraints active. We immediately know that if the constraint is assumed to be not active, then the corresponding lambdas are 0. That's easy. Now comes the situation where one constraint is assumed to be active. Exactly one. Okay? So the first option is the first one is active. The second option is this one is active. Note that this immediately means that here the other one is not active, and so on. Okay? So this is when we assume one constraint being active, and the last one in both are active. Okay? So let's explore all these options. Let's explore option number 1. So if lambda 1 and lambda 2 are 0, then these two stationarity conditions are just two equations in two unknowns. Actually, they are not even coupled. We can see if this goes away, then x is trivially 2, and y is equal to 1. Right? Is this the optimal? Well, we don't know. We have to check all conditions. So we come here and see, oops, the optimal solution violates primal feasibility. Therefore, this cannot be the candidate for the optimal form. So we have to go and explore this option. right? So what do we have here is that since this constraint is assumed to be active, this inequality actually holds with equality. Therefore, x optimal is exactly this guy here, and we can use it as a substitution everywhere, right? So then we also know that since only the first constraint is assumed to be active, the other one is inactive, so the corresponding lambda is 0, okay? So lambda 2 is 0, so that goes away. And here we have the first equation, second equation, and the third equation, which is from the activity of the constraint. Right? So we have 3 unknowns, because we have x, y, and lambda 1 as unknowns, but we have 3 equations. So we can solve the system of equations. We can find out that y is like this. If we know y, we know x. And we also compute the corresponding lambda. Okay? Now we have to check this candidate. Does it satisfy primal feasibility? Well, it does. Does it satisfy dual feasibility? Is the solution with respect to lambdas dual feasible? Are all lambdas greater or equal to 0? They are. So this solution is also dual feasible. Does it satisfy complementary slackness? Well, the second one is easy. Lambda 2 is equal to 0. Immediately this one is satisfied. Lambda 1 is not 0, so for this product to be 0, the bracket must be 0. But it is trivially 0 because we are assuming that the constraint is active. And this is exactly kind of the constraint, okay? So even the complementary slackness condition holds. So this is a very good candidate because it satisfies all Karush-Kuhn-Tucker conditions. And what? Should we go forward or not?
No, it was a quadratic problem.
It was a convex optimization problem, so we could stop here. We have found the optimal solution. But just to illustrate that even if you would go further, you would find new candidates and they would clearly violate at least one of these constraints. So how would that be done? Well, we know that this constraint is assumed to be active. Since the other one is not active, the corresponding lambda is for sure 0. We again solve system of 3 equations, first, second one, and this one. 3 equalities in 3 unknowns gives us this condition, this solution. Immediately we see that the lambda that we got is not dual feasible. This candidate cannot be the optimal point. Therefore, we go here. We say, let's see what happens if both are active. Okay? If both are active, then we know that this holds from the activity. This holds from the activity of the other constraint. So we are looking for what is x star, y star, lambda 1, and lambda 2. And for that, we have 4 unknowns. Therefore, we need 4 equations. First, second, this is assumed to be active, so there is equality, there is equality. So we have 4 equalities in 4 unknowns. We can solve that very easily to obtain this candidate. We check whether the candidate is primal feasible. It is. We compute also the corresponding lambdas. And we find out that this one is not dual feasible. Okay? So this cannot be the optimal solution. So this is how the method works, and let me leave the rest for the next lecture.